metamorphic grade, and remember that refers to temperature. So as you go to higher temperatures, you're going to start seeing different minerals forming. If we kind of zoom in on this, see if I can zoom in on some of these terms here. Yeah, so at lower grades, you'll see chlorite, maybe some white mica in the medium grades, biotite mica in medium to high grade metamorphism. Garnets start to form at higher grade metamorphism. Kyanites at high pressure aluminosilicate. Silmanites a high temperature aluminosilicate. So again, by figuring out the mineral assemblages, you can determine the metamorphic grade of the rock. Those metamorphic grades, and it's showing the pressure temperature conditions into which these form. So here we're looking at pressure. So about 3 kilobars is about 10 kilometers down. And then here we're looking at temperatures. One thing we should point out here is your book says that low-grade metamorphism occurs up to about 400 degrees centigrade. Medium-grade metamorphism is like 400 to 600, whereas high-grade metamorphism would be above 600. And so you can see that low-grade metamorphic rocks, so let's say we have a phyllite or schist over here. If we take that phyllite or schist to a medium-grade region, then we get schist. And if we take this to even higher pressures and temperatures, we can get gneiss. This metamorphic grade refers to intensity, and it depends mostly on temperature and determines the extent of recrystallization and neocrystallization. Again, remember, at higher temperatures and pressures, different metamorphic minerals will form. And so your book mentions that low-grade metamorphism occurs between 250 and 400, medium grade between 400 and 600, and then high-grade metamorphism, higher temperatures greater than 600 degrees centigrade. As grade of metamorphism increases, recrystallization and neocrystallization produces coarser and new mineral assemblages that are stable at those higher pressures and temperatures. And that's really the key thing, is that the mineral assemblages will tell you what pressures and temperatures the rock experience. And one thing we use are these index minerals, and index minerals indicate those metamorphic grades, those pressures and temperatures that we're interested in. And so low grade, one of the key minerals is chlorite, but we may get some white mica, maybe here up a plus or minus, which means you might have, you may or may not have it. You will see the andalusite, and that's, remember, that low temperature, low pressure aluminosilicate. Then for medium grade, biotite's an important mineral. You might start seeing some garnets, a metamorphic mineral called starlite, which looks like garnet, except it kind of has a longer aspect ratio. Remember, garnets are like little soccer balls that develop, right? So they're more equant, whereas this would be inequant. And then you might see the white mica. Remember, white mica is muscovite. And then you might see that higher pressure kyanite that forms. And then at highest grade, silmanite. That's a high temperature aluminosilicate. Maybe some K feldspar, garnets can be there. So different minerals. Cordierite is a metamorphic mineral that forms at very high temperatures and pressures. So it just depends on the pressure temperature condition, metamorphic zones. And so based on those index minerals, we can chart out where temperatures and pressures were hotter and highest during metamorphism, right? So in this example here, I'm showing how there's silmanite, cordierite. Well, those are high-grade metamorphic minerals. So the metamorphism was most intense in here. But as I go farther out, I see I get to lower and lower grades of metamorphism. So, and these individual lines right here are said to be isograds. So geologists have used this to map out zones of metamorphism in different regions. And I'll show you a map of that here in a moment. Idea of metamorphic facies. So remember, facies is an assemblage of minerals that define particular pressures and temperature conditions, right? So what the protolith experience. And you'll find that there's several facies. And so a set of mineral assemblages indicate certain ranges of pressure and temperature. So zeolite is a very low pressure and temperature, just above something called Diagenesis. I didn't really talk much about Diagenesis because Diagenesis are just kind of the advanced stages of lithification in sedimentary rocks, but sometimes this process involves neocrystallization, new minerals forming. So once you get neocrystallization, you're in metamorphism. So usually diagenesis is sort of bordering into metamorphism. So, but we get zeolite and this field called prehnite pompiliite metamorphic facies, which is not very common. But then the ones I want you to focus on is this one here called greenschist facies, hornfels facies, granulite facies, and blueschist facies. Also this eclogite. So what do these mean? So we'll look at the hornfels. So hornfels occurs at low pressure but high metamorphic grade. So that would occur, this number one, this line indicates the geothermal gradient as you go into the crust, how hot it is. You can see you get lots of heat close to the surface. So the only thing that can be doing that is an intrusion of magma. So hornfels is usually related to contact metamorphism, where there's a magma that comes up, a local heat source, and burns the wall rock, right? And so number one here, contact thermal metamorphism, right? So that's very common in the high Sierra Nevada. You go up to Tuolumne Meadows, the top of the magma chambers up there, the batholith, and you'll see some of the rocks are burned, and those are the contact metamorphic aureoles, these halos that occur around these metamorphic rocks, or that occur around the igneous intrusions. So hornfels is an important one. And then greenschist is usually a medium grade, a normal pressure metamorphism. It's common to a proximity to a magma chamber. So, for example, the Sierra Nevada, the batholith was hot, but as you go through the Sierra foothills, you start encountering, like if you go to Auburn, Colfax, you start seeing metamorphic rocks that fall in this greenschist facies metamorphic zone. So they experience some temperature and also some pressure as well. So here number 4, number 3. Well, here number 4 is some stable continent interior and a collisional mountain belt. Well, like a convergent margin, right? And phyllite facies is just a little bit higher temperatures than greenschist. Key thing you start seeing is hornblende crystals here. Whereas greenschist, you'll see chlorite and a mineral called actinolite. When you get to granulite facies now, these are the higher temperatures. You'll see high pressures, medium to high pressures and relatively high temperatures, right? So these can occur, again, in the collisional mountain belts, like at the bottoms, near the bottoms of the batholith. And volcanic arcs could be another one, right, where they occur. So really high-grade metamorphism. Another place where granulite is common is, again, collisional mountain belts, like under the Himalaya. You got so much rock up there, deep burial, high pressures, high temperatures. The other important one that I want you to know about is this blueschist facies. So blueschist is where you're taking rock to very deep pressures where there's not a whole lot of temperature. Well, you must take cold rock, and that's old ocean lithosphere. So these are common to subduction zones. Here it says accretionary prism. Well, that's a subduction zone, right? So when you see blueschist metamorphism, the mineral we see here is really a blue mineral called glaucophane. Glaucophane, there's also a mineral called lawsonite that forms in these blueschist metamorphic environments. So when you see blueschist, it's synonymous with subduction zones. So blueschist metamorphic belts commonly outline ancient subduction zones. And here in California, we have mountain ranges here and the coast ranges that are all composed of blueschist rocks. So we know that we have an ancient subduction zone here in California. In fact, there's a ridge just south of Hollister called Glaucophane Ridge, and glaucophane is that blue mineral of the blueschist metamorphic rocks. Also, eclogite is a medium to high temperature, high pressure metamorphic rock, which is also common to subduction zones, but now we're just getting to a little bit more temperatures here, deeper burial. What's unusual or unique about the eclogite is that they do have garnets. Remember, garnet's a little bit higher temperature, but they also have some of those blue minerals that occur in the blueschist rocks. So now, continuing on here, this is a map of basically the New England states, and we're seeing these different metamorphic zones, right? So higher grade would be the quarterite. So it looks like intense metamorphism occurred here, but around there we see there's silmonite around there, silmonite quarterite, and then as we go to silmonite muscovite. So all these are charting out the different metamorphic zones that occurred in this region. And so these would be the isograds, the contacts between these different colored bands here. Let's look at the types of metamorphism. That would be the next. And so usually we talk about two. We talk about the thermal, which is contact metamorphism, and then we talk about the regional metamorphism, which is large, kind of wide extent region, right? So regional metamorphism is, remember, oro is mountain genesis, so making a mountain. So orogenesis is you're making mountain belts. So regional metamorphism is common to mountain belts, collisional mountain belts, convergent margins, subduction zones, all those features. Whereas contact, here they call it thermal, but I usually call this contact metamorphism, is where there's a local heat source and there's an intrusion. Other metamorphisms include Barrow Metamorphism. So if you have a basin where there's subsidence and there's more and more compaction, the geothermal gradient will cause metamorphic reaction to occur, and you get Barrow Metamorphism. Dynamic metamorphism occurs along fault lines. So if you get shearing along the fault lines, you might get a rock called myelinite. I'll talk more about that in a moment. And then hydrothermal is usually occurring at mid-oceanic ridges, where you're seeing hot fluids alter the rock in that region. Subduction, well, that's a blue schist, right? High pressures and low temperatures, blue schist metamorphism. And then you might get meteorite impacts that'll come in and cause this metamorphism to occur, right? And so the key thing, you get these rocks called tektites and shocked quartz grain. Go back to these types of metamorphisms, just to kind of focus on these a little bit more. And the conditions vary in that the geothermal gradient may be different, right? The geothermal gradient may be hotter at magmatic arcs, right? Cooler under Kansas, right, where it's going to be different, right? And then for the rocks may endure different types of pressure and temperature conditions. There could be shearing or compression in some, others will not have that. And the extent to which rocks interact with these hydrothermal fluids will vary. So 3 reasons why there's different types of metamorphism. So we talked about this contact metamorphism. Your book also calls this thermal metamorphism. And here we can have a local heat source, like an intrusion of a magma, Pluton, and the heat flows from that magma to the wall rock. And you get this metamorphic aureole, right? And we call those roof pendants. So usually you'll see these roof pendants that surround these intrusions. Then there's Barrow Metamorphism, which I talked about, the subsiding basin, where once you get down to 8 or more kilometers, you start seeing that neocrystallization. Remember, dynamic metamorphism occurring along a fault, usually at depth where the rock behaves a little bit more plastic-like or ductile, and you get this rock called myelinite. And myelinite's usually fine grained because the rock's been sheared along that fault line. Then the important one here is regional metamorphism. This is covering a large extent region. The heat source is variable, and this occurs under compressional mountain ranges, convergent margins, and the protolith experiences 3 changes. So there's heat due to the geothermal gradient or the igneous activity, like the batholith, right? So proximity to a batholith could be one of these. You endure greater pressure because of Barrow, so that's a confining stress, right? Or maybe you undergo compression or shearing. Well, that's a differential stress, right? Where you get the foliated metamorphic rocks. So foliated rocks are really common to these types of regional metamorphic settings. And then the shock metamorphism is where you're getting these tektites, which are basically the rock or minerals that are shocked from these meteorite impacts. And the quartz experiences a phase change into a more dense form called coesite.